Okay, hello back. Sorry, I had to interrupt here. I had to check something out myself. So, where were we? We wanted to get index positions and also for the second row and third row and so on. And for all the horizontal lines. And the way I wanted to do this is to take this 6x4 block of starting positions and adding for each one of them this offset vector. Okay. So how to get this starting vector is like this, and for taking this as starting positions, we would need it in this form, and now we can do this chot construction. Let's try this. We have to bracket this here. Okay, so now what has happened is for every element in here it has added our horizontal vector. Okay, and we can see that we still need to subtract 1. Let's do it this way. And this form looks a bit strange. So we can see here's a second layer, and this is because this expression has a vertical dimension. So if we remove this vertical dimension, we get the shape we want. Okay, so this is this here. We don't want this down arrow here. Okay, so let's construct our index area here further. And add the vertical four lines. So we could just copy this and the starting positions for the vertical lines are like this, and to connect these two we use this symbol. It's called catenate along first dimension. Okay, we know the shape now. So this is our old, and this goes along the first, along the rows. So this looks like it has worked, and now we need still the diagonals. So expressions of this form give a matrix, and we would only need the diagonal of this matrix. And luckily there's a nice expression in APL that gets us just that. This time without a vertical dimension, so we don't need that. And let's see. take this, if we add this to our list, so the starting positions are in a 3x4 block for the diagonals. Let's check. Yes, seems alright. And for the anti-diagonal, so these four numbers, we would just take this expression and mirror the matrix, flip it around the vertical axis, and then take the main diagonal. This gets us the anti-diagonal. So this would be our index, our list of indices. Let's check. 69. There are 69 four rows on the board, so this seems correct. So now it would be nice to have a board and check it. Okay. So because like this we can't tell if it has if it takes all the rows correctly. So now we need a function to throw stones in, and they fall down, and then test our indices. So such a function would look like this. We add to the board in column number 4 stone 2, for example. So we've already seen how this works, and now the next stone would have to go here. So we have to determine this position. Now there's a nice function again. So we need the position of this 0. There's a function in APL that gives us the first occurrence of a number. It gives us the index here, and we can use this if we take the appropriate column. So this column is a vector now, and as this index function works from left to right, we need to reverse this first, and now use our index search function sorry, and get this position 2 that we need. Okay, and since we invert here the y direction, we would take 7 minus and set this to 1, for example. So this works. Let's check also for an empty row. Yes, works too. Let's check for this row again. Okay. So in order to make a function out of this, we can write it this way in APL: board x stone and return the board. So add board for 1 returns this. Okay, so these are so-called D functions. They just take omega as a list of arguments, and we can with one single arrow here assign them to 3 different variables: the board, the column or x position, and the stone value 1 or 2, and just put it here. This is just a separator for expressions, and the last expression is automatically the return value. So if we want to modify the board, we would just do it like this. Now it's constantly modified. Okay. Again. Okay, so now we have a nice board already. Now we could try our indices, and we see it has read out here these values. I don't remember exactly. Okay, I think yes, the top part was the anti-diagonal part. So these first are 0, and then comes the 1 here, and then one with 2 here. So this seems correct. Okay. Okay, so next we have a function to add stones, and we have a way to read them out. Now maybe we need next we would need a way to calculate a value for this for a player. Okay, so I want to use a very simple value function that just takes the number of stones in each 4 row, and if it's 1, 2 and 3, this is the points. These are the points for this row, and if it's 4, of course it's a win. So this would be 1000. Okay. add these points for the player and subtract these points for his opponent. So first of all, we need a way to see if the stone is 1 or 2. So the player that's on the move, at the move, or his opponent. And this is very easy again in APL. We just write this, and it puts a 1 where this area is 1, and here it puts a 1 where it's 2. Okay. And to calculate the points now, we just need to add these 4 values for every row here. So this should give a 2 here, for example. And again, this is automatically done very elegantly and nice in APL like this. It automatically adds along the rows and returns a vector with all the results. And for player 1 this would look like this, and for player 2 it would look like this. And of course only rows or columns should count that have only stones of 1 player in it. Okay, so for example in this row there's 1 stone of this player and 2 stones of the other player, so nothing can happen here anymore. This row is lost for the game. So we should only take rows where the other player has a 0 in it into account. And the way we do this is, let's say, call this VS, and so this takes only the rows of the other player where the player at that's at the move has a 0 count, and vice versa. This would be for the other player. And now we can just add this to get the points. So the player S has 16 and the other player has 17 points in this case. This doesn't take account the rows that are filled with 4 stones yet, but we will soon see this. So already we have functions here that we want to keep and save maybe. So we want to make a namespace now, and this is easy. Just do it like this. Make a namespace and change into it, and now we can edit functions here. So let's have a main function that we call to start the program, and let's test it. So if we call main now, yes. Okay, and put everything there now, our add function and our index list. So copy this and put it in there. Let's call it int and add. There was our add function. Copy it. Put it in there. And now we have our point function. Points for a board and a player. Okay. So we had this calculation. Yes, I think I can remember that. Sorry, I'm still a bit ill, so sorry for all the noises. We take our board B and get all the 4 rows, and then we check if the player is if the value is the player, call this yes, or if it's the other player. Now, how do we determine the other player? There's a nice way to do this. We just index this array with the player. So if s is 1, it gets us this value, and if s is 2, it gets us this value. So this is automatically the other player. And then we have said that we only take the values where the other player is 0, has 0 stones in it. So these would be the points for the player. And these would be the points for the other player, and then we return the points for the player minus the ones for the other player. And this is the sorry, the way it looks. in APL, return value of a function, the arguments, and some list of local variables. Int is a global variable, and we can try this now. We just set a board up and call board. Okay, our test. We need our test function. So let's add board for 1 and 5, 2 and 4, 1 again, and calculate. Okay, I forgot to set this. This is of course necessary. Let's calculate for player 1 the points. So just call main, and player 1 has 12 points in this setting. We could check this now. So 1, 2, 3, 4, 5, 6, 7 and 9, 10, 11, 12. Yeah, seems okay. So what next? Maybe I make a cut here and cut this together. So see you.